Okay, welcome back to Chapter 2. We are talking about atoms and different properties of atoms and elements. Most of the energy in an atom, or a lot of the energy in the atom, is going to be held in electrons. And electrons are going to be organized in different energy levels. They're going to want to start filling the lowest energy level until they get more energy in the next shell. And then if they have to go to the next shell, each energy level is going to have increasing levels of energy. And they're going to be as lazy as they can be. They're going to be in the lowest energy level that they can be in. Energy is the capacity to cause change. Potential energy is the energy that matter has because of its location or structure. So electrons in their different shells, that is energy that it is holding because of its location. This is potential energy. An electron state of potential energy is called its electron shell or energy level. You can think of the energy levels in the different energy shells as a ball on different steps. So a ball on a lower step has the ability to fall a little bit and release a little bit of energy. A ball at the top of the steps can fall down more steps, and by the time it gets to the bottom, it can really be falling with a lot of energy. And that's the same thing with electrons. They start off in lower energy levels, but they can be pushed up into higher energy levels. Most of the chemical behavior of an atom, the way it's going to form bonds and the way it's going to react to other atoms, is going to be determined by the distribution of electrons in its electron shells. So we already saw the importance of protons in determining what the atom is. Protons and neutrons determine how much an atom weighs. If you change the number of neutrons, you change its weight. Electrons are tiny. They don't affect any of those things. But the number of electrons there is going to determine the energy and bonding patterns of that atom. The periodic table of the elements shows the electron distribution for each element. So if you go through it, 1 electron in hydrogen is going to be in its first shell. 2 electrons in helium are in its first shell. That's all that it can fill. And then if we go to a lithium, its first shell can hold 2, but it has 3 electrons, right? Atomic number of 3. It's going to have 3 protons and 3 electrons. So it has 2 electrons in its first shell. That third electron has to go to a second shell. It'll have 1 electron in its second shell. That second shell can hold up to 8 electrons. So beryllium, with an atomic number of 4, is going to have 2 electrons in its first shell, 2 electrons in its second shell. Boron has 2 in its first shell, 3 in its second shell. Carbon, 2 in its first shell, 4 in its second shell. Nitrogen, 2 in its first shell, 5 on its second shell. Oxygen, 2 in its first shell, 6 in its second shell. Fluorine, 2 in its first shell, 7 in its second shell. Neon, 2 in its first shell, 8 in its second shell. So 8 in its second shell, that is going to be filled. That means if we come to this third row on this partial periodic table, the sodium is going to start filling up its third shell. So everything in this third row, the first and second shells are filled. Then sodium is going to have 1 electron in its third shell. Magnesium will have 2 electrons in its third shell. Aluminum will have 3 electrons in its third shell. Silicon will have 4 electrons in its third shell. Phosphorus will have 5 electrons in its third shell. Sulfur will have 6 electrons in its third shell. Chlorine will have 7 electrons in its third shell. Argon will have 8 electrons in its third shell, and that makes it filled. So one thing to pay attention to is when we're looking at the different rows in a periodic table, you'll notice that first row, the top row, has 1 shell. The second row has 2 shells. The third row has 3 shells. If you were to look at the whole periodic table, the fourth row has 4 shells. The fifth row has 5 shells. If you also look at a periodic table, hydrogen is at the top of column 1. Everything in this column, hydrogen on down, has 1 electron in its outer shell. Beryllium is in column 2. Everything beryllium and down has 2 electrons in its outer shell. boron is in column 13. So we don't see the whole periodic table here. If you were looking at the whole periodic table, boron would be in column 13. And boron and everything in that column below it has 3 electrons in its outer shell. Carbon and everything below it has 4 electrons in its outer shell. Nitrogen and everything below it has 5 electrons in its outer shell. Oxygen and everything below it has 6 electrons in its outer shell. Fluorine and everything below it has 7 electrons in its outer shell. Helium and everything below it has a filled outer shell. For helium, that means 2 electrons in its outer shell. For neon and everything down, that means 8 electrons in its outer shell. In class, we're going to talk about how to draw these electron diagrams, how you can figure out how to draw them all. If you're not in class, please make sure that you get comfortable with that. You may need to go through some of these videos that are attached here. You may need to look up some on your own. Something like Khan Academy might help you figure that out. Each electron shell can hold a maximum number of electrons. So we just went through that. The first shell, the max is 2 electrons. Second shell, max of 8 electrons. The third shell, for the atoms we talk about, it's 8 electrons again in that third shell. Some weird things with some of them that can go up to 18, but we're not talking about those things. Up to 8 electrons in the third shell. The valence electrons are electrons in the outermost shell. And those valence electrons are very important. So, you assume the inner shells are just filled with electrons. But how many electrons are in that outer shell, that valence shell? The chemical behavior of an atom is mostly determined by the valence electrons. Electrons with a full valence shell are chemically inert. So if we look at neon here in the bottom, it has 8 electrons in its outer shell. Neon has a filled valence shell. It is not going to react with anything. Things like argon and krypton and helium, they have a filled valence shell. They're in that last column on the periodic table. They're called noble gases. They are chemically inert. You won't see them forming molecules. And because of that, they're not very important in the chemistry of life because they don't form molecules. They don't do reactions. They're just there. They're cool. They can do some cool things, but we don't actually see them making molecules. Okay. An orbital is a 3-dimensional shape where an electron is found 90% of the time. Each electron shell consists of a specific number of orbitals, and no more than 2 electrons can inhabit a single orbital. So the first shell has 1 orbital, so it can hold 2 electrons. The second shell has 4 orbitals, so it can hold 8 electrons. And after that, 4 orbitals give you 8 electrons. Some craziness kind of in some of those, but we're only dealing with the things that have 8 electrons in their valence shell. The reason why valence electrons control a lot of the chemistry of atoms is because atoms want to have a filled valence shell. So those noble gases, that last column, their valence shell is filled. They are complete and happy with life, and they don't feel the need to change anything. Atoms that only have 1 or 2 electrons in their valence shell might just get rid of it, or they might share it so that they feel like they've got a filled valence shell. Atoms that have maybe 6 or 7 electrons in that valence shell are going to share or pick up a couple to feel like they're filled. So atoms with incomplete valence shells can share valence electrons, or they can transfer valence electrons to other atoms. And these interactions are going to result in atoms staying close together, held by attractions called chemical bonds. So hydrogen, if you remember, hydrogen has 1 proton, 1 electron. That electron, it has 1 electron in its valence shell. So 2 different hydrogen atoms, each has 1 electron in their valence shell. They're going to come together and share those 2 electrons. So that is going to make each atom believe that it has 2 electrons. It has access to 2 electrons. So at that point, it feels like it has a filled valence shell by those 2 sharing with each other. That's a chemical bond. When the valence shell is filled with electrons, the element is not reactive. So at that point, hydrogen, H2, is going to be when valence shell is filled with electrons, that last column on the periodic table, They are inert. They are not participating in reactions. We already discussed that. A covalent bond is sharing a pair of valence electrons by two atoms. So what we see with these two hydrogen atoms, they each share one electron. So they are sharing two electrons in total. So they have a single bond. By each of them contributing one, they both feel like they have two. Each shared electrons count as that atom's valence shell for both atoms. A molecule is going to be two or more atoms held together by covalent bonds. If they are each sharing one pair of valence electrons, they are each donating one to that bond. It's a single bond. So here in hydrogen, H2, we see each one sharing one. In a double covalent bond, or what we see here with oxygen, O2, they're each contributing 2 electrons. They each have 6 in their valence electron. Each oxygen has 6 valence electrons. So they have 2 electrons are each going to share, and by that they feel like they have 8 electrons, so they feel like their valence shell is filled. That's a double bond. So here in water, what kind of bonds are we seeing here? Oxygen and hydrogen are each sharing 1 electron, so that's a single bond. And there's another hydrogen, oxygen and hydrogen are each donating 1 electron to that bond. So it has 2 single bonds. What about in methane, CH4? Look at this structure here. You see a central carbon bonded to 4 different hydrogens. A carbon is donating 1 electron to each of those bonds, and each hydrogen is donating 1 electron to the bond. So we see 4 single bonds. You can draw it in this model that you see under the electron distribution diagram. You can do these Lewis dot structures where each dot represents an electron, so you can put dots for each electron. Or you can put a line to represent each pair of shared electrons. So H-H means each hydrogen is sharing a pair of electrons. O with 2 dashes and O means each oxygen is sharing 2 pairs of electrons. The space filling model shows you what it would actually be like if you blew up that atom to a size that you could see. The notation used to represent atoms and bonding is called a structural formula. So it's H/H. Often though, you are just going to see it abbreviated with a molecular formula. So H with this lower 2, a subscript 2. That subscript always refers to the number of atoms before it. So H2O means 2 hydrogens, 1 oxygen. CH4 means 1 carbon, 4 hydrogens. Let's watch this little clip about
bonds. A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
Okay, so at this point, the first part of this video, you could calculate atomic mass, atomic weight. You could tell me how many protons, neutrons, or electrons something had. You could tell me the difference between an element and a molecule. In the second video now, you can tell me what a covalent bond is, the difference between a single covalent bond and a double covalent bond. Even if I asked you what a triple covalent bond is, you can induce what that type of bond would be. You can draw a dot structure to show where electrons are in an atom, and you can tell me how many valence electrons an atom has. You can tell me if it is a noble gas, that it's inert, or if it is not a noble gas. If it doesn't have a filled valence electron shell, you could tell me that it's prepared to participate in chemical bonds. Okay, atoms in a molecule will attract electrons to varying degrees. So sometimes some atoms are a little bit more attractive and electrons are going to hang around it a little bit more. And electronegativity is how much an atom has that attraction for electrons in a covalent bond. Oxygen and nitrogen tend to be our most electronegative atoms that we're going to deal with. The more electronegative an atom is, the more strongly it pulls shared electrons toward itself. So if we have this molecule of water, oxygen is more electronegative than hydrogen. So the electrons are more attracted to oxygen because of that electronegativity. So that means the electrons are going to spend more time around oxygen than they do around the hydrogen end of water. That means, if you remember, electrons have a negative charge. There's going to be not a complete negative charge, but almost a negative trend. It's going to trend towards a little bit negative on the oxygen's end of that molecule. Since the electrons are spending a little bit less time on the hydrogen end, they're going to trend a little bit positive. We're going to indicate that if you see this little like squiggly thing, that's a delta. So there's a delta minus on the oxygen end and a delta plus on the hydrogen end of this molecule, indicating that the electrons are spending a little bit more time on that oxygen end. The electrons are moving the entire time through the entire molecule. They just are a little bit more time at that one end. This is going to be very important by the end of this chapter, and when we talk about water, this electronegativity is very important in how molecules interact with each other. So really make sure you understand this concept before you move on. This is going to result in two types of covalent bonds. There is a nonpolar covalent bond where atoms share the electrons equally, and a polar covalent bond where one atom is more electronegative and the atoms do not share the electron equally. So when you're talking about nonpolar covalent bonds and polar covalent bonds, which one would you say that a molecule of water has? You can see that it is not sharing the electrons equally. The oxygen is more electronegative. The electrons are pulled a little bit towards the oxygen end. So that is a polar covalent bond. That makes water a polar molecule. The unequal sharing of electrons will cause a partial positive or partial negative charge for each atom or molecule within that polar molecule. Sometimes an atom can strip electrons from the other one. So one example would be sodium chloride. Sodium with its one valence electron is not really interested in trying to form 7 bonds to fill its valence shell. So it just gets rid of that valence electron. When it gets rid of that valence electron, that means that the next shell is its valence shell. So it feels like it has a filled valence shell and it is perfectly happy. Also, by losing that negative charge, by losing that electron, it is left with a positive charge. Chlorine has 7 valence electrons. So if it sees a little electron floating around, it's going to grab that and fill its valence shell. That means that chlorine is going to have a slight negative charge. Those atoms with a charge are called ions. So sodium atom has no charge. It has 1 valence electron. Sodium ion has a positive charge. It has lost an electron. Chlorine ion has a negative charge. It has gained an electron. Positively charged ions are called cations, and negatively charged ions are called anions. Those words are pronounced a little bit differently from how they look like they would be. A cation and an anion. So make sure those are comfortable words for you. Opposite charges attract. So that positively charged sodium and the negatively charged chloride ion are going to be attracted towards each other. That forms an ionic bond.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, we just discussed these words. If you remember, these are words you need to know. A cation is a positively charged ion, and anion is a negatively charged ion. Cations and anions are attracted to each other through their opposite charges and form ionic bonds. A compound formed by an ionic bond is called an ionic compound. These are often also referred to as salts. Salts are often found in nature as crystals because they'll form this sort of lattice crystal shape as positive and negative charges are attracted to each other. One quality of ionic bonds and of ionic compounds is they break apart or dissociate in water. So if you took a crystal of salt and dumped it in water, you're not going to come back the next day and see a pretty crystal of salt in water. You're going to see a cup of salt water. There are also some weak bonds. Individually, they're weak, but when they add up together, they're very important in holding the structures of molecules and of organisms. Weak chemical bonds are important. Many large biological molecules are held in their functional form by weak bonds, and the reversibility of weak bonds can be an advantage. So one is a hydrogen bond. If you remember talking about polar molecules, here we have a partial positive charge on a molecule of water and a partial negative charge on the nitrogen end of ammonia. That partial positive charge of hydrogen is attracted to the partial negative charge of nitrogen, and so that kind of attracts those molecules together. Hydrogen bonds, therefore, do not form molecules like we saw with ionic and covalent bonds. They are not strong enough. These do not form a new molecule. And these are reversible, so that bond is there, but then the electrons move and the bond dissociates. So these are weak, but important in attracting these molecules, different molecules together. A hydrogen bond forms when a hydrogen atom covalently bonds to an electronegative atom and is attracted to another electronegative atom. In living cells, electronegative partners are usually oxygen or nitrogen atoms. These are very important in holding together DNA and holding together proteins into their correct shape and giving them their functional properties. Some molecules are not polar, they are nonpolar, but electrons are still moving all around it. And as a result, you'll just randomly have random partial positives and negatives. And those will result in van der Waals interactions. So if electrons are distributed asymmetrically in molecules or atoms, even just momentarily for a fraction of a second, they may accumulate by chance in one part of a molecule. Those van der Waals interactions are attractions between molecules that are close together as a result of those charges. Individually, these are very weak. Those electrons are constantly moving, so that interaction is only there fleetingly. Collectively, they can be strong, so they are helping this amphibian, a gecko or something. Its feet are able to cling to a wall, and it can scatter up a wall because of van der Waals interactions. So the strongest bonds we see are covalent bonds. The strongest are triple covalent bonds, then double covalent bonds, and single bonds. Then ionic bonds. Ionic bonds are pretty strong as crystals or solids, but are weak in water. then hydrogen bonds and van der Waals interactions are the weakest bonds we see in living interactions. But don't be fooled here. Just because they're individually weak, collectively they hold a lot of molecules together. Let's pick up here with our third part of the video. I will see you in just a moment.